So for where is it? Okay. So we had a ladder resting against a wall. And we had all the forces on the picture. One was the frictional force. It was called F. One was the normal force due to floor. Normal force due to wall was called P. There is the wall end is frictionless, so there is no friction on that end. The length of the ladder is given as 10 meter, right? This is what you have, and the angle made by the ladder is 53 degrees. Right? And the center point of the ladder, the weight is acting downward. That is the weight of the ladder, which is given as 50 Newton. This is what we had. I think we did work on it partly. We worked with the forces. So we worked on the first, and we needed to find mu s for the floor and the ladder. Right? The weight of the ladder is given. We know that it is in equilibrium, that it is at rest. It's not moving, slipping. It's sitting against the wall. We worked on the summation of forces, and we came up with the equation N will be equal to mg. That means it's also going to be equal to 50 newtons. Correct? Upward forces are equal to downward forces. As we can see very clearly, N must be equal to this force. Right? These are the only two downward forces. And F should be equal to horizontal forces. This is from the vertical forces. From the horizontal forces, we can get P is equal to F. Correct? Good? This is where we stopped in last lecture. Now we needed to use the second condition for the equilibrium, which is the torque. And that says the sum of torque should be equal to 0. And we decided to pick a point. We could use pretty much any point. We could do the talk about this point, we could do the talk about this point or this point. However, the point where the forces, maximum forces are acting, that is the point you try to pick so that most of the forces give you a 0 torque. That would make the calculation easier, which is this point which has two forces acting on it. So taking the torque we have to do work with the torque only for this and this. Correct? Is that right? What about the torque due to friction force? About, I don't know, what did I call this point? O? So due to frictional force, what's the torque of the friction force? 0. About that point, what's the torque due to normal force? 0. Because the line of action of the forces, they pass through the axis of rotation or the point of rotation. So torque will be 0. Moment arm is 0. This will have a torque. It has the ability to rotate. That is also has the ability to rotate. Correct? Now what do we need for it? This force multiplied by this length. Correct? If I extrapolate it, this force multiplied by this length. Is that right? mg, this is the moment arm. For mg. This is the moment arm for P. Right? Now if we know those lengths, we can write an equation for torque putting the counterclockwise torques and the clockwise torques together. Now, the first force would be 50. Now, tell me what this length is going to be. We know the length of the ladder, weight always at a center point. What is this length? 5, right? We know what is this 5 or 10 making with the horizontal, 53. Can we tell what is this length? Yes, this would be a 90 degree, this is 90, this is 5. What would be this length? 5 cosine of 53. Make sense? This vertical length would be 5 sine of 53. We are not interested in it because we are only interested in the line of action of the weight and the axis of rotation and the distance between them. Now for P force, you are here. You are looking for this length. Can we figure this length out? Now it should be easier. Do we know what this angle is? Sorry? 90 minus 53? Is that right? If we know that angle, can we figure out this? That would be plus P 10 cosine of 37 equal to 0. Now, which one of them is positive and which one of them is negative? Both cannot be positive, otherwise there would be a net torque in it. One of them has to be positive, one of them has to be negative. So, what kind of torque this mg is producing? Counter or clockwise? Counterclockwise or clockwise? Clockwise. It's negative. What about P? It's counterclockwise. It's going to be positive. Can you solve for P? You lost. Yeah. But did you get how did we get the numbers?
Yeah.
You understood? Okay. Right? This is what I got. Good? All right. Everyone good so far with the directions, with the numbers? Now, using the previous equation, we already know P is equal to F. We have already found P. That means F is also equal to 18.8 Newton. Right? Because P is from the horizontal balancing of forces. We know P should be equal to F. We know F is static friction is mu s times N, 18.8. We know that Fs from this equation is less than equal to mu s N. This is an old formula that we use for static friction. And we know N already. So mu s would be equal to 18.8 Newton divided by 50 Newton. You divide them, you will get the value for mu s, which was the physical quantity. It's 0.38. 0.38, which makes sense because we know mu s is most of the time is the value which would be small less than 1. Now there are some problems. I believe there is at least one problem in the homework which is similar to it. However, in that problem there is someone standing somewhere on that ladder. That would change, that would shift the forces. It would add one more force. So if somebody is standing, let's say here, you will have to, if there is a man standing here, you will have to take care of that weight value too, according to the vertical force. But the whole procedure remains the same. Okay, you will just add up another force in the form of that person who is standing somewhere on the ladder. This question is very important for examination point of view. You will not see it as a part of multiple choice question. You will not see it as a short question answer. You will see it as a proper long problem if you see it. Now, several occasions we mentioned a point, but we never really defined. So like here I said, this is the center of that ladder and the weight should be acting downward. Now, we always had this point in our problems, but we never really pointed it out as a center of mass. The objects have a center of mass or center of gravity. So if you have a mass, how it is defined? It does have a mathematical definition. If the object is made up of multiple points, any object you are dealing with, you're talking about a cube, maybe you're talking about a sphere, maybe you're talking about a car or some very irregular shaped object, the masses, it will be made up of masses, right? Small masses. They all are at a certain distance from a common point. For example, I draw this picture. There is one common point which is the center of mass. If you pick this mass component which is m1 at distance at point x1, y1, you pick another mass from it, it could be x2, y2 and so on. These are different mass particles which made up it. So we can have the mass starting from m1 to infinity, which make up the whole mass. If you add up all the mass components, mass particles, they all will make the total mass of this object. Correct? These all are at some distance from a common point. The center of mass is given as, if I define it separately for horizontal, xcm given by m1, x1, m2, x2, and so on, divided by the total mass. Y, center of mass, y component m1, y1, m2, y2 plus so on, divided by m1 plus m2 plus so on. Okay, that means you have divided your mass into small mass pieces and figure out the distance of each mass piece from the center of mass, add them together, that would give you the x component of the center of mass and the y component of the center of mass. Both of them make a common point which is called the center of mass. If there is a z, if there is a third axis z component, that would include to that as well. In statistical language, this one is defined as center of mass is, okay, so I'm not going to write the whole thing. Center of mass is mass. Now, those who understand the statistical language better, for them this definition will work. Average position of particles. How do we find the center of mass of any object, not necessarily a regular object? If the object is irregular, that usually is performed using calculus. You can divide the mass into multiple masses, find out how the distance varies, and then you can apply the calculus and find out the center of mass. But for some masses which are very regular, we already have some idea about it. The geometric center could be their center of mass. For example, when you are dealing with a sphere, do you know where the center is? If it is a continuous distribution of mass, if you know that everywhere the density is the same, where would be the center of mass? What's the geometric center of a sphere? It is its center. Its center. That center would be its center of mass if it is a continuous distribution, if density does not vary. If you have a cylindrical object like a can, where is the geometric center? Somewhere here. That is also center of mass. If you have a cube, the center of a cube is the center of mass. Sometimes the symmetry axis for a disk, the symmetry axis is passing through its center. So center of mass would be the center of that disk. Where is the center of mass of the donut? What do you think? It may not be on the donut. Yeah, the central hole. Yeah. What's the center of mass of a meter stick? Half of it. If you put unequal masses on that meter stick, for example, you have 0, 100 centimeter, so it should be at 50 centimeter. If you hang a mass equal to maybe 5 kg here, and then you put a mass equal to 2 kg here, will center of mass of the whole system shift? Yes, which way? Sorry? Towards a bigger mass. It would be somewhere here, which can be determined using the same formula that we used here. Okay, when we talk about the sun and earth rotation, the center of mass of this system, which comprises of sun and earth, that would be more centered, that would be closer to the sun because of the mass. There is a way, there is a small derivation with this formula using the same picture that I had there. If we found if the system is in equilibrium, the sum of torques will be 0. So the total torque of all the points M1G, M2G plus so on multiplied by XC, that would be equal to individual torque of each mass particle, so on. They should be equal to each other. Do you see the difference? For the torque, I have put the G with it. Why? Because torque involves the forces. The force related to each mass component is the weight force. So basically you are looking at the weight of individual particle, which is M1G, M2G, and the mass. So XCM would be equal to M1, X1, G would get cancelled, M2, X2, and so on, divided by M1 plus M2. We should be able to write it as this, summation. Mi Xi divided by okay. Similarly, we can write each one of them. You can write the XCG. Sometimes you might see XCG center of gravity or center of mass. They both are the same thing. When you are talking about the center of mass, you are looking at just the masses multiplied by the distances. When you are looking at the center of gravity, you are looking at the weight of each particle about the center of gravity. So we can also write YCG or YCM equal to summation YI divided by MI. And Y, if there is a Z axis, Y VCG equal to MI VI divided by. Okay, complete center of gravity or center of mass would be equal to X CG, Y CG, and Z CG. No.
I know we haven't done much with Z in this class.
We are not going to use it separately unless we are dealing with a certain problem where you have to find the center of mass of a system. Other than that, this has to be introduced because whenever we talked about any object motion, you throw a mass as a projectile in the air, it's a center of mass which is moving. We were always taking the velocity of the center of mass, not the individual masses. So here we put them together, that okay, this is the center, everybody has a center of mass to it, and when that body moves, we are dealing with the velocity and the acceleration of that center of mass. Okay, so initially where you had v, velocity for any object, you actually have the velocity of the center of mass. We just never really mentioned it there. Exactly. Because that's a valid question. Which mass particle are we talking about? When we are talking about the car moving, are we talking about the front of the car, middle of the car, back of the car? Which part are we talking about? It's made up of so many particles. Yes, it is indeed made up of in so many particles, but they all are considered as one center of mass. The whole mass or weight is acting at that center of gravity. And we are talking, so when we had any object moving, so sometime you might have noticed that if I had a circular object, I put a dot in the center. And when I drew the distance, I drew the distance like this. This dot has moved here. From here to here, distances. You always take distances or the velocities due to the center of masses. Okay, not the individual particles. Okay, unless the mass is so huge and it's not a rigid body, okay, and the individual particle, they are too far from the center that you cannot really consider it as a part of one body. You will take it as a whole object, and the whole weight is acting at one point, which is the center of gravity. Okay. Any questions? So velocity of the center of mass can be given as m1 v1 plus m2 v2 and so on divided by same formula. Now velocity, since we take the velocity as distance over time, so if you divide both sides by the time, you will get the formula for velocity. We can also multiply if I multiply this on this side, the total mass VCM, that would be equal to m1 v1 m2 v2 plus so on. This tells you the momentum of center of mass is the sum of momentum of individual particles. And this is what we have been using before, right? When we defined that MV equation, we talked about the whole mass of the system. We didn't divide it into individual particle. But there could be some cases where you do need to divide the system into individual particles. Now, there could be a question why there is a need to define it this way. For example, you have a system where you have individual masses, two masses, and they both are rotating about certain rotational axis. Here, and if they are connected by a rod, and that rod has a negligible mass, but this one has a small mass m, this one has a big mass m. On such system, you have to talk about the momentum for the overall system, where you're going to treat this one as one particle this one as another particle, but still they will make one big system. So you have to divide them in two. So in such cases, we do need to have this kind of explanation. Okay, center of mass of this system is not necessarily going to be on any of the masses. It's going to be somewhere in the center, right? Probably closer to this one. So when we are talking about such system, when you have two masses separated out, but you are treating it as one system, but you can still deal it with the similar object, one object made up of two particles, which will have a common center of mass.
So we might want to use that common center of mass, that particular velocity is not as accurate as the particle.
For system, there will always be one velocity. There will always be one acceleration, as long as you have a center of mass to a system. And especially we are moving on to the rotation. In rotational, for rotational problems, you will see a lot of problems where mass will be distributed. Okay, masses will be at different distances from the center, and then you will have to put them together. Okay, and you can add or subtract accordingly. This will start making more sense as we move on. Okay, it has to be introduced before the rotational motion. Like I said, this is one complete system, but it has two particles in it.
And it has a specific center of mass that are not on either particle.
Yes.
So they have their own individual momentum as well.
They will have one combined. They will have individual momentum and one combined momentum.
And so we're saying that the individual momentum add up to the system.
Exactly. Yes. Yes. Yes.
So we use the center of mass is whenever we talk about rotation. Like this is all rotation.
Mostly, yes. Okay. And that one has its own reason, which I think I'll introduce later. Ready for the quiz? Oh, be ready. There is just one topic left for this chapter. That's a stable equilibrium. It's just going to take few minutes next lecture, and then we can start the rotational motion.
So when are we having the
We are not having exam before the holidays. Okay.